Well, good afternoon. Should we get started? Welcome to the December meeting, the Science Engineering Council. Happy holidays, everybody. Hopefully, with this weather notwithstanding, we'll have a really nice, fun holiday. We will do that a little bit. It's that time of year for memberships. Thanks, everybody, for having signed up for another year. And if you know anybody, feel free to refer them to us at the Science Engineering Board. The three of us here, particularly to reach out to Cheryl in the back and get more information about it. We're here second Wednesday of the month. And also for your scholarship foundations, donations, another amazing contribution that you can make that helps directly into the community. So with that, want to also put out a plea for help finding speakers. We've got lots of room for speakers in the calendar starting February. And also a plea to help us at the board. If you want to be a board member or join as a committee member, or if you know someone who would enjoy that, please do reach out to anyone. Okay, so I'm going to announce one upcoming meeting, and then I'll turn it over to Mary to introduce Justin for today's topic. Next month in January, we're going to have Dr. Tristan Nelson from the UCSB Department of Geography. Her research focuses on active transportation, think bicycling, and the use of big data and analytics to better plan our cities. And she's very active in analyzing our South Coast transportation system, in particular around bicycling and other active mode of transportation. So looking forward to that discussion. Again, we have happy to hear any ideas for other topics in our upcoming months. Let's see. I think with that, Mary, I'll turn it over to you. If you could give us Justin, please.
Thank you, Tim, and welcome to today's talk by Professor Justin Wilson. He's newly at UCSB at the chemistry and biochemistry and chemistry department. And my husband did an awful lot of work to clean out some laboratories so he'd have some space to work. My husband's recently retired, so it's Peter Ford from that department. We're very pleased to have Justin. He's come from Cornell University, where he first started as an assistant professor in
chemistry and
No, I know. What year?
oh,
Yeah.
2015. 2015, yeah.
Yeah. I'm getting to the point where I think things should be in the 1990s and not in something. Justin has a PhD from MIT and worked on, among other things, platinum anti-cancer drugs. And the reason that's of interest to me is that I worked with the same fellow when he was at Columbia and did some of that clinical work. So that's of tremendous interest to me, obviously. He went from MIT to Los Alamos National Labs. And that's probably what piqued his interest in rare earths. And what we're going to hear today is what he's doing with heavy metals and how, if we bind them properly, they have applications in nuclear medicine. And also in taking those rare earths out of I think I'm right about that. So I'm now going to turn it over to Justin and let him tell you what it does.
Thank you very much for this introduction. And thanks, of course, for the invitation to be here.
Let's see if I can get the screen shared over here. Oops.
Oh.
Yeah. We have feedback still.
Yeah, turn up your maybe we should see.
No, I see.
Speaker to down low, mute your microphone.
Okay.
There we go.
Yeah.
All right, thank you. Yeah, so as Mary mentioned, my research program is in the field of developing what we call chelators. Chelators are a form of chemical compound that bind metals. And in today's presentation, I'm going to give you guys kind of just a brief overview of two research areas that we've been looking at in terms of how we have been using these molecules called chelators and some of the applications thereof. And I recognize, of course, that I don't know how many chemists are in the audience, but feel free to interrupt if you have questions or clarifications, and I'll try to keep things at a general level. We'll probably show some technical data, and I'll try to walk it through on a more broader and general level if there's any kind of confusions or questions. So we'll start with kind of the introduction here, which is the idea of like what metal ions look like in solution, right? And so I'm starting with the kind of the simple picture, right? If you take a metal and it's dissolved in something like water, you basically have all these water molecules that are actually bound and attached to that metal ion. And so that's what it looks like when you have something like, sodium chloride in water or calcium in water. These water molecules will bind directly with them. And we typically think of this from a couple different perspectives, right? When we have metal contamination in solution, like in the incidents of like Flint, Michigan, several years ago, there was lead that was leaching from the pipes that was being dissolved in, and so that's obviously a bad thing because these heavy metal ions, depending on what the type of metal ion is, they can bind to things like proteins, which is represented with that figure, and kind of inhibit their normal function. We also think about metals and heavy metals from the perspective of them being environmentally harmful, right? So things like radioactive metals like uranium and radioactive waste are examples thereof. So part of the way that we approach some of these challenges here is to develop molecules called chelators. This is, again, a chemical structure of an example of probably the most common chelator known currently. Those dots represent electron pairs, and basically what happens is that this molecule will effectively wrap around the metal ion, displacing all those waters, and it forms basically like this claw-like complex. It captures a metal ion, and the key feature here is that when we capture this metal ion, we now have changed its properties from the free metal, which is in this little aquated state with all the water molecules, to this new, what we call a coordination complex. We've changed the overall charge, we've changed the hydrophobicity of the metal. And so in essence, by designing these chelators, that gives us the capability of controlling what these metal ions are doing and where they can potentially go. And what we've been doing in our lab is trying to develop these chelators to apply in these two problems. The first problem is in the field of nuclear medicine. This is a picture of a patient who's been treated with a radioactive drug. And so again, it's nice because you can actually see what's going on in that patient in a relatively non-invasive way. And then the second picture is a picture of individual rare earth elements that have been separated. And so I'll start by talking about our efforts in rare earth elements. First, I'll introduce a chemical structure that I would say is of key importance to us in our research group. So I showed that one chemical structure of the chelator called EDTA, which is the most common chelator. This is a chelator that we've been working with extensively in our group. And the major difference between this chelator and the previous chelator that we mentioned, EDTA, is that this one actually will bind to large metal ions like rare earth elements very effectively. And again, to belabor the point, that's a fairly unique property among these metal ion chelators. Something like EDTA, for example, would be quite ineffective at binding to large metal ions. And thematically, we're going to see that the problem of rare earth separation and chelation and nuclear medicine chelation lies in the realm of trying to capture these very large metal ions at the bottom of the periodic table. So these are the rare earth elements, and this is a periodic table, and the pink highlighted elements are examples of all these rare earth elements. The one thing that I often like to highlight here is that, it's kind of a funny region of the periodic table because you can actually get a chemistry degree and go many years through your bachelor's without even like talking about this region of the periodic table, right? We don't, at least I guess I tried to teach it in my Gen Chem class this fall, but if, the average experience is one where the instructor tells you not to worry about all these elements at the bottom of the periodic table, right? And so what's changed is that there's been a lot of technologies that have been developed, right? So, for example, if you pick up your smartphone, there's some different rare earth elements within your smartphone, and this is used for batteries and for optical displays. These rare earth elements have very unique properties compared to other metal ions on the periodic table, and that's given rise to a lot of these technological applications. The other area of rapid expansion here has been within the electric vehicle realm too, right? So same type of deal. There's over 8 different types of rare earth elements within each of these electric vehicles that are important for the batteries and the motors and things like that. And so with all these new technologies that have been arising, there's been a real big demand to obtain and have these rare earth elements in high concentrations. Where do we get rare earth elements? For many decades, we were getting a lot of them actually locally here in California. This is a mountain pass mine that's on the border of Nevada. I think this is actually on the way out to Las Vegas. There's a lot of rare earth elements that are naturally deposited here. The picture is fairly informative, I think, because you can kind of see the impact here of the mining operation, right? This is not necessarily a pretty operation. I'll talk more about that momentarily. But what changed in the mid to late 80s is that rare earth production in Mountain Pass site basically stopped to a large extent. At that time, I think there was the perspective that the rare earth elements, the cost and effort of obtaining these rare earth elements from this mine did not give enough payoff for the value of the rare earths at the time. And so a lot of the rare earth production efforts were discontinued in Mountain Pass site. There were efforts, I think, maybe 10 years ago to revamp Mountain Pass as a mining site, but I think those have been largely abandoned as well. And so as a consequence, one country did not stop processing and mining rare earths, and that was China. And so the current state of the art right now is that China basically has a global market of rare earth elements kind of pinned. And that's a consequence of a couple factors. This is actually a really nice recent article from Scientific American in the December issue, and these are some graphics that I took from there. But it shows you in kind of a three-dimensional plot what the production rate is of rare earth elements, or total production of rare earth in China versus US in red, and then the rest of the world. And so again, you see that China over this time period has been making the lion's share of the rare earth elements globally. Now, the other thing that's relatively informative to see is that there's actually quite a lot of rare earths around, right? So these are the amount of reserves as of 2025. Again, China is a box in yellow, US is a smaller box here, and then Brazil is another box up in here. And so one key point here in a general sense that rare earth elements from a raw abundance perspective are actually not that rare, right? So things like platinum and gold and palladium and silver are actually more rare in the Earth's crust. The major challenge and limitation with the rare earth elements is just simply related to the challenge in mining and separating them into their individual elemental constituents. And that's been the limiting factor, right? So with the situation in China, they've had now decades to build up the infrastructure, the local expertise for these types of mining and separation operations, whereas the US has kind of lagged behind. And so going back to this slide, one alternative approach, right? So there's this intrinsic challenge in that if we want to get rare earths from the ground, this is a very environmentally damaging process. The other challenge is that once we get those rare earths, we have to actually separate them into their individual components. So what I mean by that is that when you get a deposit of rare earths, they all kind of stick together. And so from a chemical perspective, you have to figure out how do you separate europium from terbium. And it's a very challenging and kind of environmentally costly process because these elements are so similar. And so one approach and one thing that we've been thinking about somewhat in our group is, are there ways actually to take the waste that we currently have, right? Your iPhone when you're done using it, or the electric vehicle that gets totaled in a car accident. We actually use some of this electronic waste and try to re-isolate the rare earth elements that way and get them in their pure form. So kind of a more circular economy and kind of a green approach to re-isolating these rare earth elements. So what's done currently in the state of the art is as follows. So these are the two processes that are typically used to separate rare earths. This figure up here, this row here, is somewhat informative because what this is showing us is it's showing us the actual size of the individual metal ions. So again, you can think of these metals as actually being different spheres of different radii, effectively, right? They have different sizes. And the one thing to point out is that the sizes of these rare earth elements are actually all quite similar. And that's one reason why why these separations are difficult from a chemical perspective. And so the two major processes are liquid-liquid extraction and chromatography. Liquid-liquid extraction is typically applied in the industrial setting for rare earth separations. The way this process works is you have two mixtures. You have a mixture of an organic solvent, something typically like kerosene, and then you have an aqueous solvent. And so you have this basically like you think of it like a salad dressing mixture where the oil and the other layers are separated. And so with this liquid-liquid extraction, you get a very small enrichment of one rare earth into one phase through each of this kind of shaking process. Now, the shaking process is done on, hundreds of thousands of liter types of vats, and industrially, we get enrichment factors from each cycle of about 1%. And so there's typically at least 20 to 50 of these different liquid-liquid extraction separations that are required to get pure elemental rare earths. And so you can imagine for each one of these, if you're generating, several hundred liters of kerosene as waste, that's problematic from an environmental perspective. But that's really the best way we have right now. The other approach is a chromatographic approach, and this is used typically on a much smaller scale. I'll show you some examples of where we're trying to adapt this to a larger scale separation or extraction. So that goes back then to what we've been doing in our lab. What we've been trying to do is we've been trying to make chelators that are attached to solid supports. And so if we think back about that original picture that I showed where we had that chelator grabbing and binding that metal ion, one thing that we've been very interested in is can we put those chelators onto a solid resin support so that if you have a solution of metals passing through the resin, chelator could grab the rare earth element as it's passing through. And so we've been doing various chemical modifications to make this happen. And this is just a very chemistry heavy slide showing what we've been doing here. These are the examples of the chelators that we've been applying. And again, this is an experimental, what we call an X-ray crystal structure. And it shows very clearly that, what's happening at the molecular level is indeed the metal ion, which is sitting in the middle, is getting fully captured and encapsulated by this chelating ion. And so with that, we've been able to put this chelator onto a solid support. And that's actually what this picture shows right here is that the depiction of the solid resin material that has our chelators that are designed to capture these rare earth elements. And so here is an example of how this process is effective or works. But in this experiment, what we can do is we can take a mixture of rare earth elements in solution and we can pass them over our resin. And what we're looking at in this experiment is the efficacy by which those rare earth elements capture the efficacy by which the resin captures those rare earth elements. You can see in this particular case, we get a preference for what we call the light rare earth elements over the heavy rare earth elements, which is basically a design feature of our chelator system that I think we actually like in our system. In terms of how we've actually been applying this in an industrial setting, we've been collaborating with a company in Ithaca, New York called Regen. They have they have a technology that's based on biology. And so within their technology, what they're actually doing is they're actually using bacteria and they're using the secretions of bacteria as a means to dissolve electronic waste. So in other words, they're culturing all these bacteria. The bacteria are naturally secreting molecules that can bind to and capture metal ions. And so they can take the solution, or they call it a biolixiviant, soak their electronic waste in that biolixiviant, and then they could grab a bunch of metal ions from that electronic waste. So the potential limitation with their approach and where we've come into this project is the fact that their biolixiviant is actually not that selective for the rare earth elements. So they also extract a lot of other metal ions. And so using our resin, we've been developing kind of strategies like this where we have our solid chelator support resin in this column here. And this yellow solution right here is the biolixiviant. This is the bioleachate from what the bacteria are producing and dissolving from the electronic waste. This biolixiviant particularly is from automotive waste slag, right? So it's actual a real sample of waste slag. And we can pass the biolixiviant through the column and capture the rare earth elements. Here, the green are the rare earth elements, whereas the red are kind of the non-rare earth elements. So the enrichment looks okay, but what's actually really nice here is that we can take advantage of the fact that the rare earths bind to our resin much more effectively. And so we can basically use a dilute acid concentration to then remove all of the non-rare earths much more selectively. And now we can get a much more enriched rare earth fraction. So this is a pie chart that shows basically how the process works. Yeah.
Is the goal separating rare earths in general from the other ones, or of the rare earths separating those into the individual elements?
So in this case, that's a great question. Yeah. So I think the larger goal is both. In this case, for this particular project, Regen wanted us to simply enrich the rare earth fraction entirely, right? And so this is more of a how do you get the rare earth out from this more complex mixture. But ideally, and I think I'll show an example in the next set of slides where we can do individual rare earth separations as well. The pie charts here show basically the enrichment. So this is basically the metal concentration in the initial biolixiviant, and you can see that there's a lot of aluminum. The rare earth content in the pie here is only about 5%. So if we do the adsorption and stripping step on the column, we can get our enrichment. This is cerium and this is lanthanum. This is praseodymium. So we get enrichment up to like 20% of the metal content. And then if we do an initial iron selective precipitation, we can get an enrichment that now is close to 50%. So we can go for an enrichment from 5% rare earth metal content to like close to 50% in this complex mixture using this chelator adsorbed resin, which is a pretty nice feature. I'll tell you one more story in the rare earth field, which is related to another chelator that we've been using. This is just, again, the structure of a derivative of that original ligand that we called macropop. What we have shown over here are the equilibrium constants or the binding constants for the different rare earth metals. And so we can really focus on the trace in red here. What I want you to see is that there's a difference between neodymium. This chelator binds to neodymium very effectively, whereas dysprosium, which is over here, binds to much less effectively. And so this is potentially an interesting feature because neodymium and dysprosium are two of the rare earth elements that are components of permanent iron magnets. And so when you think about recycling electronic waste, there's a real great need and desire to separate neodymium and dysprosium from one another. And so what we figured out actually is that rather than doing a complex liquid-liquid extraction to separate these two metal ions, we can actually use a very simple precipitation in an aqueous solution. So the general idea here is that if you have a mixture of these two rare earths, neodymium and dysprosium, in water, you can add a chelator like glycine macropop, and then you could add a counter ion that forms an insoluble rare earth salt. So you can see here you get an insoluble rare earth salt. It's a cloudy solution. Now, what's interesting here is that because glycine macropop binds to neodymium more effectively than dysprosium, the thought or hope was that the precipitate could actually be selective, right? Perhaps the neodymium would get bound much more tightly and the dysprosium would be allowed to get precipitated as a carbonate salt. And indeed, if we do EDX analysis, we can see that that's the case. So this is a X-ray spectroscopic analysis of the precipitate. If you do the precipitation in the absence of a chelator, you get an equal molar mixture of the two rare earth metals, which makes sense because if you just have neodymium and dysprosium, you add a precipitating counter ion, they both drop out. It makes sense. But if we do the precipitation now in the presence of our chelator, we get a substantial enrichment of the dysprosium in the precipitate compared to neodymium. And that's a consequence of the fact that the chelator can bind to neodymium and prevent it, kind of hold it back from getting precipitated, whereas it binds to dysprosium much more weakly, and that allows the dysprosium ion to drop out of solution. Yeah.
So what causes this favoritism for one versus the other? Is it the size in the middle of the chelator? Is that the big molecule?
Yeah, yeah.
Or is it the chemical composition of the chelator where the mouth is for holding the metal?
So that's a good, I think it's a good and a complex question. So for this particular class of chelators, we've done a lot of work on them thus far, and systematically, and I kind of alluded this early on, one of the unique properties of this chelator class is that they preferentially bind the larger ions over the smaller metal ions. And so, of course, why is that? I think our interpretation is as just a size-based fit into the macrocycle. We can actually compare, if you want to take all the slide here in a moment, where we'll actually look at the crystal structures of two differently sized ions, and you can see how the macrocycle is much more symmetric for the large ions compared to the small ions, kind of signifying that it's got a much more relaxed conformation.
But the size difference of those across the lanthanides, they're so percentage wise, they're like within a percent, right?
Right.
But you don't see that separation. I mean, in size, it's like a little difference, but then the preference is not. It doesn't crack exactly.
Yes.
Right.
Yeah, that's right. And then I guess that's a good point. Is the nice thing about trying to do a neodymium dysprosium separation is that they're actually, I think, 4 or 5 elements apart from each other. So there is a more, they're not adjacent rare earth, in other words, right?
Right.
That's a much more challenging.
But even 4, that the diameters are.
Yeah, it's maybe about 2 to 4% difference there. Yeah. So we do see these subtle differences in the affinity, right? And this is where, designing chelators to try to optimize these size preferences can be really valuable, right? And we've been trying to develop a program on that. How do we fine tune a chelator for specific sizes? So it's an interesting chemical problem to think of for sure. So basically the conclusion here is that we can get separation via a simple aqueous-based precipitation of neodymium dysprosium. We can, of course, then extrapolate this. Like, this is permanent magnet waste. This is waste powder right here. And this is after we dissolve it. You can see that there's a much higher concentration of neodymium compared to dysprosium in these magnets, which is expected. And we can do the same precipitation process. And in doing so, we can get a very high separation factor from this magnet waste directly, right? So we can get a separation factor of 420. That means we get a 420-fold enrichment of the neodymium and dysprosium, right? So it works well. And I get the point here, right? You can see actually the blue color. The blue color is from copper, which is a contaminant, right? And the concentration is pretty high. And so another nice thing about these chelators is that they're kind of agnostic to a lot of competing metal ions. They have a real preference for the rare earth metal ions. So that allows us then to focus on the separation problem more specifically. Right. So I was going to switch directions for the next couple of minutes if there's any more questions about rare earths, or we can come back at the end on the rare earth topic. Yeah.
How do you release the rare earth atoms from the chelators, and does that destroy the chelator, or is it like a one-time relationship for atoms?
The easiest way to release is actually just to drop the pH, so make it more acidic. And so what'll happen is that the protons will compete for the metal. Now that's, one would argue that's a potential limitation of the system too, but it's a common limitation, I would say, right? So you still have to use acid to liberate the metal. The chelator stays intact though. And so like what we've actually done, we've done recycling studies where we can, do the precipitation separation, acidify it, recover the chelator, and use it for a subsequent step. So, I think over the next couple of minutes, I'll give kind of just a brief story on, how we've been using these chelators for nuclear medicine. And what I'll say here is that the area of nuclear medicine that we got really interested in early on in our group was this area called targeted radionuclide therapy. So when a lot of us think of nuclear medicine, we think of things like a PET scan, right? You go to the hospital, you get a PET scan, and you see you're diagnosed a disease, or maybe some of you had a stress test for cardiac health, or you go on the treadmill and you get a radio tracer to see how your heart's looking. Those are forms of diagnostic nuclear medicine. What's fundamentally different with this targeted radionuclide therapy is that it's a form of nuclear medicine that's therapeutic. So this is a real patient from a clinical trial in Germany. And the idea and concept here is that you can, in principle, administer a radioactive drug into that patient, so something like intravenously. By virtue of the way that that drug is designed, it will localize to all of those black dots with our metastatic tumor lesions, and the radiation will get deposited locally. And in doing so, it'll destroy those tumor metastases. And so again, this is a pretty remarkable image because this is actually a real patient from a clinical trial in Germany who received a radioisotope called actinium-225 that I'll talk about here momentarily. So again, you look at this and to a certain extent, it looks like magic, but from a chemistry perspective, we can kind of break it down. What do we need to do to design a radioactive drug that can actually accomplish this? First thing we need to do is we need to have a way of delivering that radioactive drug to the tumors. This is typically by attaching the metal to something like an antibody or a peptide. So cancer cells often have receptors that are overexpressed compared to normal cells that will bind to peptides or antibodies with much higher affinity. So it's a way of getting a high degree of selectivity via these receptor recognition motifs. The second component is the radionuclide itself, right? And so here we want to have a radioactive isotope that has an appropriate decay half-life. You can't be like 1,000 years, right? Because that's too long. It has to have the right type of radioactive emissions in order to destroy the tumor cells. And then the other kind of the second or third concern is you have to be able to actually make it on a scalable amount. And that's actually, we can talk more about that later, but that's actually one of the big hurdles, I think, I would argue in this field. So the third component is what we do, right? We actually try to make the chemical glue that holds the radioactive isotope to our delivery, right? And so this is pretty important. This is what we call the bifunctional chelate agent. Our approach there is basically making these chelate agents, the things that bind and tightly retain these radioactive metal ions, and we attach it to a targeting vector. That allows the targeting vector to bring with it the radioactive payload that can then destroy the tumor cells. And again, this is pretty important if you think about it, because if this complex, this chelator complex is not stable.
Thank you very much.
Basically, oh, is there a question? Maybe next sentence. The whole concept basically doesn't work because the radioactive isotope will fall out and then kind of go where it wants to and cause all sorts of off-target side effects. There are several different ways that we could use radioisotopes for treating cancer. I would say most commonly over the last few decades, there's been a lot of use of the beta particles. So beta particles are high energy electrons that deposit radiation. So as an example, Novartis and a couple other drug companies have had 2 drugs approved based on lutetium-177, this beta emitter, very recently. One's for neuroendocrine tumors and one's for, I think, metastatic prostate cancer tumors. The other approach is to use alpha emitters. Alpha emitters are radioisotopes that emit alpha particles, which are much more massive. So we're talking orders of magnitude more massive than beta particles. And so the fundamental difference here, if you want to draw an analogy, is like a beta particle would be taking like a high power rifle and shooting it through a wall. You do like, a bullet hole worth of damage through a lot of walls, right? This is reflected by the large penetration range of the tumors. But the alpha particle is like shooting a cannonball through the wall, where it goes a much shorter distance, but you're doing a lot more damage and killing a lot of those cancer cells much more effectively. This is a return to the periodic table showing how there's a lot of isotopes all across the periodic table that have therapeutic applications. And the major point here is that, again, we have a lot of isotopes that are at the bottom of the periodic table, right? And as you go lower on the periodic table, these metal ions get larger. And so this is where the chelators that we work on, which are known to bind these large metal ions quite effectively, are very, very promising. And so this is the slide that we showed already. This is the macro-PA chelator that we talked about. What's unique about this is that, again, it binds to large metal ions with larger ionic radii more effectively than small metal ions with smaller ionic radii. And that's a feature that we have been exploiting for the nuclear medicine as well. So this chelator, for example, can bind all sorts of different radioactive metal ions with therapeutic applications. So it can bind to this radioisotope bismuth-213, which is an alpha emitter. It could bind to radium-223, which is another therapeutic alpha emitter. And then it could bind most notably to actinium-225, which is a very large alpha emitter, which is the same radioisotope that we saw from that clinical trial in Germany. And so the binding to actinium-225 is actually very effective, right? In that if you take a sample of actinium-225 and you treat it with this macro-PA chelator, the complex will form almost instantaneously. And the other benefit is that once that complex forms, the actinium really remains tightly bound and captured by this macro-PA chelator so that it can't escape. And so with that in mind, what we've been able to do is we've been able to attach macro-PA to targeting vectors to actually deliver actinium-225 to various different tumor devices. And so this is a lot of work that's actually been in collaboration with John Babbage, who's now the CEO of Ratio Therapeutics. The idea, though, is that we can combine basically three components here. We have a chelator, which is our macro-PA, which will bind the actinium-225. This chemical moiety right here binds to prostate-specific membrane antigen, which is overexpressed in, yes?
Is this what you're outlining here? I mean, there's lots of insoluble compounds or ways to bind those elements, but this sounds like it's the only way to do it as opposed to like an organometallic, because you're having to do organic chemistry to bind it to those other sites that are going to be targeted where you want it to go and not just everywhere. And so, right, because you can't really make an organometallic of that as opposed to a chelating agent. So this is almost like there's no other way to do this, is there?
No, so you're saying, I mean, here the general approach, you have a chelator, you have the covalent attachment, and then this is basically the organic stuff that targets it, right?
Right.
And so you're saying that an organometallic approach would not be.
Well, yeah, because it looks like I can't picture out any other way you could do what you're trying to do is get that active alpha emitter to where it needs to go.
Mhm.
Right?
There's
Because you'd have to make an organo.
this is yeah, I would argue that this is the best way to do this. What's actually interesting is that there's the only therapeutically available alpha emitter right now on the market is actually radium-223 dichloride, and it's actually administered as a dichloride without any kind of chelator. And so the idea there is that the radium, again, it's a very different concept, but the radium looks enough like calcium that will naturally localize to bone metastases. So you're very limited in that type of approach because you're banking on the natural localization properties of the metal ion. Whereas this approach, we're saying, okay, we're gonna, here's our delivery agent, and we need to drag the cargo with us through the chelating agent. So again, I would argue that this approach is a lot more versatile because we can, this binds to prostate-specific membrane antigen, but we can also put that on an antibody that might bind to like a HER2 receptor for breast cancer or something like that, right? So there's a high degree of versatility for different diseases that one could exploit with this approach, in my opinion. Yeah.
So how does one administer such things? You use a targeted injection?
These are
This would be easier in some parts of the body than in others, obviously.
well, these are systemic injections, so it's typically IV, and that's because the real so I would say for decades there's been for decades there's been local radioactive source. So brachytherapy, for example, is very common for prostate cancer. You basically put a radioactive seed near the prostate. This type of construct is designed to target metastatic disease, which is really disseminated. And in that case, you don't have a fight, right? You can't just, here's a radioactive seed, right? The tumor mets are just everywhere, right? So it really has to be a systemic injection. And then in that case, it circulates and the targeting vector and the receptor affinity can bring it to the site where it needs to be. It's also, I would argue then it's also the other form of radiation therapy that we often think of as external beam radiation therapy, right? So gamma, and that also you need to kind of know where the tumors are in the first place. This systemic injection, you get the benefit of trying to find all those metastases.
But the beam, obviously, a certain type of cancer, your body can be tattooed, and that's where the beam is.
Yeah.
Is located in order to find the tumors within.
Mhm.
I guess my fear with the systemic is that something happens that it breaks down and it goes someplace it shouldn't.
Right, right. That's a concern.
Yeah.
The the thing I argue about the radioactive stuff that I think is really beneficial is that, that, for example, let's talk about the half-life. The actinium-225 half-life, 10 days, right? So you get a distribution or off-target effect, and
Then the rest of it, yeah.
10 days is going to be gone, right? So
Yeah.
you talked about platinum chemotherapy a little bit early on, right? So I actually, one of my uncles received platinum chemotherapy for testicular cancer when he was in his 20s, and it's a very effective form of therapy. But I remember once he came visit me in the lab, in Steve's lab, and we took a sample of blood, and we found platinum in there still,
Of course.
decades later, right? So with this, you only have a 10.
What's in the kidney?
Yeah, yeah. So it's pretty remarkable, right? But with the 10-day half-life, I mean, I guarantee you won't find actinium
Yeah.
decades later.
Yeah. Okay.
They are, these are concerns too, though, right? So, and again, part of these concerns are what we're trying to do, right? The concern of it breaking down, well, part of that is, well, how tightly can we bind the metal ion so that it doesn't break down, right? So this is a chemical problem that we're working on.
Yeah, I guess that was part of my poorly worded question because I never thought I've heard of chemotherapy obviously for decades, but like I never thought of how you would get it to where you want it to go. And then as far as the decay chain, it's going to turn into another element.
Yes.
Of course it is.
Right. And so are those picked like as opposed to polonium 210, something that would not be so, the decay chain would take it to something that's not so bad? Because it's probably going to release, right?
Yes. So yeah, we're talking about interesting physics here, and I like it. But with radioactive decay, there's a phenomenon known as recoil, right? Which is conservation of linear momentum, right? So you have an isotope, you emit an alpha particle, it jerks back like a shotgun, right? And so it turns out the energy that it jerks back is on the order of hundreds of electron volts, which is way, ton of energy if we're talking on a chemical scale. So the daughters are, we have to concede that the daughters are just going to break, fall out. I think the way that we circumvent that is we have to choose the isotopes strategically based on their decay chain. So one thing, if you looked at the decay chain, the half-lives of those daughters was all fairly short, right? So once you get that initial decay, as long as you're not decaying to a half-life, several hours or days, you don't have much time for redistribution, right? You get kind of sequential decay. So that's kind of I think the way that at least a lot of us think about that problem and how we can kind of overcome that. It's choosing isotopes with the right decay chain. So yes, this is just an example of mice with prostate tumors. So you get really good uptake. This is 14 days, 21 days post-injection of these mice with prostate tumors. All of the radioactivity is localized to the tumor, so it's really effective. The macropa chelator, there we go, is actually being commercialized right now by Ratio Therapeutics. So we've got this trademark name. What is nice is that the macropa chelator has been adopted by all sorts of other research groups across the globe in terms of approaches for actinium-225 based radiotherapy. And what's even more exciting is that over the last year, that macropa based constructs have entered clinical trial, and these are actually actinium-225 therapeutic trials that are sponsored by Bayer Therapeutics. And so again, it's a really nice example of how this whole concept of making chelators can actually play a really important role in a larger context of drug discovery efforts and nuclear medicine in this particular case. And so this is just kind of a last slide. I mean, there's a lot of chemical structures, but this is what we do because we're a chemistry lab and we like to make molecules. But the idea here is just that, what we've been doing now for the last 6 to 10 years has been trying to make improvements to the macropa chelator. And that's actually been pretty tough to do. I think we found kind of the best one really early on, but we have some other ideas in terms of what types of radioisotopes we're targeting and addressing for this concept. And so I think that's pretty much a good way to summarize talk, and I'd be happy to open up to discussion more so. But the general idea, right, is that we've been using these chelators that are unique because they bind to large metal ions over small metal ions. And we've shown here in two capacities that we can use this chelation concept for both the extraction and separation of rare earth elements, which are these critical minerals that are only going to get more critical, especially with the tariffs and the weird geopolitical situation in the world right now. And in addition to that, we've also shown that these chelators have biomedical relevance, primarily in the context of nuclear medicine. And so that's bearing important out now in a couple clinical trials that are underway for these macropod-based constructs. And so this is a picture of my research group. The funding for this project has been NSF and the NIH, rather the Department of Energy for the rare earth stuff, and then the NIH for the biomedical applications. And again, I'm very happy to sit here and have more conversations and discussion with you all. And thank you once again for the invitation to come out here.
Hey, Robert. Go ahead.
Oh, yeah. Hi. That is absolutely fascinating. I'm curious, can this chelation process be used to extract rare earths from seawater without having to do mining?
That's a great question. Yeah, we have I think the seawater question really depends on which seawater deposits have high enough rare earth concentration. So in seawater, we're starting to get very, very low concentrations. And so it becomes a much bigger challenge to try to extract those. In terms of what I've seen in the literature, I know that people have used chelators for extracting things like uranium from seawater, which tends to have a higher concentration. And there's been some recent efforts to look at lithium extraction from seawater as well, too. Again, the challenges here with the seawater situation is just that it's a huge factor of dilution. The metal concentrations are a lot lower. So it's certainly, I think it's a challenge that would be surmountable with really good chelators.
Thanks.
That leads me to follow up with that question, which is there a lower limit in terms of concentrations? I mean, there comes a time when you don't want to waste your chelator.
Mhm.
So is there, what do you consider a lower limit of concentration to begin with?
For actually wanting to do an extraction process.
Yeah.
It's hard. I guess it's hard to say because I think we typically think of extracting either from solid state materials that we digest or maybe directly leaching from the solid state materials. There's the whole techno-economic analysis that goes into the consideration of seawater extraction. But again, I can't really comment strongly on that. I mean, there are like we could use lithium as an example. Like I think the amount of lithium in the ocean is far surpasses the terrestrial lithium. But the problem is that there's so much ocean, right?
Yes.
So
Yeah.
how do you get over that? I think these are challenges that chemists and chemistry can address.
They get a lot out of that, the geothermal. I was reading down by Salton Sea, that you pump water in and you get crazy brine out. And I hear that has a ton of lithium in it. So maybe your source might be, but the question I had was, obviously AI, have you thought of applying this search for new chelating agents to come up with new structures that would be fun to make?
Yeah, we just had a seminar speaker that I hosted at UCSB who talked exactly on that topic. So there's people thinking about that. The funny thing I'll say is that the seminar speaker had their AI predicted structures, and one of the structures of one that we actually have made already. So artificial real intelligence, we kind of came to the same conclusion in a way, but I do think it's a very,
because there's a new call out for DOE has a full disclosure, we're DOE. That is for using AI for cool stuff.
I mean, I think this would be a nice application in my opinion. Yeah. So
Claire has a question. Yeah.
I'm just wondering if you've looked at adding like fluorescent moieties or anything to be able to create a scintillator or something, capture the metal, detect it that way.
yeah, I guess the short answer is we haven't yet, but it's the idea of putting some sort of sensor and, using that as a readout to see rare earth concentrations, maybe you could, we've had, we've had people reach out to us with, oh, here's a bag of rocks. What is a rare earth concentration? If you could figure out, if you had a high throughput way to do that, like on field samples, I can imagine that'd be valuable rather than having to, lug around an ICP or something. So that would be a nice application, I think, for these systems too.
Do we know whether China is doing research into electronic waste recovery?
I'm sure they are. Yeah, I'm sure they are. I've seen papers out of academic labs, but I know they also have a pretty lengthy international patent literature in there too. So. Yeah, the China, right? The environmental regulations are so lax that they,
Yes.
they question economics at that point, whether more cost effective to do e-waste or just continue mining.
Any other questions? Okay, thank you so much.
Thank you very much.